The next one I want to talk about is for people that are going to be working to design either electrical or mechanical systems. So we're going to call this example 3.1.1. This is a prereq to a prereq, actually. So we'll say that this is, we'll start with a concept of an undirected graph. An undirected graph G consists of two finite sets. N and E. The set N includes a list of objects called nodes or vertices. In this class, when we're talking about directed and undirected graph, I will try my absolute best to focus on calling these things nodes. Vertices usually imply that that we have a Cartesian coordinate system imposed on every single node. So the concept would be that, like, did you recognize in the last example for computer graphics that every vertex had an actual coordinate system, had like numbers associated with them? That doesn't have to be true for graph theory, but it can be true. So when we're using graph theory to talk about connectivity between joints in a bridge, not only will we have connectivity between different places in that bridge, but we will also impose a frame of reference so that we're looking at the actual dimensions of the bridge with respect to the materials that are built. However, in electrical systems and electrical networks, we can use graph theory to model the topology of the network, to model where resistors are connected, where voltage sources, current sources, and all that stuff. Does the size of a resistor matter in terms of connectivity for local analysis? I'm not talking about transmission lines, but I'm talking about like when you breadboard a circuit. For those of you, nobody's taken this classes before? Engineering 37? Okay. Does the length of a resistor's leads matter? No, you don't need topology in that. You don't need those vertices there, right? So for now, I'm going to say, when we're talking about general graph, undirected graphs, and we don't impose Cartesian coordinates, we'll use the word nodes. If we imply that we want to use actual coordinate systems to do that, then we'll talk about those as vertices, right? Okay. So that's the list N. The set E will be called the set of edges, and includes a list of sets with two unique elements. Each edge will be called, in this case, can you guess if it's going to be called directed or undirected? Undirected. An undirected edge. Let's see. So let's create an example using this setup. Let's take a look at a graph, quote unquote graph, with 4 nodes and 6 edges. What does that immediately mean about the set N? How many elements does it have? 1, 2, 3, 4. If I have 6 edges, how many elements does the set E have? 6. In this case, because it's undirected, we're going to use sets in order to talk about connectivity between nodes. So in this case, we'll say U1, U2. The next one we'll say is U1, U3, U1, U4, U2, U3, U2, U4, U3, U4. How many total edges do we have? Yeah, 6 edges. Let's enumerate. So I guess 2 things that I want to call attention to. Notice, for undirected graphs, each edge is what? Is modeled as a set. Why does that matter? Yeah, there's no order. It's not an ordered pair, hint, hint. It's not an ordered pair. In set theory, does it matter which one I label first and which one I label second? The only thing that matters when I'm talking about sets is inclusion, right? Each of these edges now tells us connectivity between our nodes. Which nodes are connected? Node 1 and 2. Node 1 and 3. 1 and 4. Each edge has exactly 2 nodes, and in this model we say that no node is connected to itself. There's another, yeah, we'll talk about that in a second. There's another matrix, where the incidence matrix we're going to construct on this one is kind of special in that way. Well, in this case it happens to be the whole cross product, but yeah, in general the edges will be a subset of the cross product. Yeah. I think in this case it's actually not the cross product of n with itself, because in that case you'd have 1, 1, 2, 2, 3, 3, 4, 4. Yeah, yeah. You'd have 6, it must be 16 elements, right? And we only have 6 of them. Yeah, and they're not ordered pairs, that's right. Yeah, yeah, yeah. That's a big one. Okay, so the other thing that we're going to say is let's enumerate these edges. What does it mean to enumerate? Could you guess, if we listed them in that order, which one we might choose as our first one? Yeah, U1, U2. What's the second one? U1, U3. And let's go all the way down to the end, which is E6, which is U3, U4. Notice the entire setup that we've had here is all set theoretic, right? Everything that we've done in this situation is to encode the graph using set theory. Every concept image that you're working with in this class, what am I encouraging you to do? Not only do you have a verbal description, not only do you have a symbolic description, but also try to visualize it, right? Visualize it. So in this case, a good way to visualize this graph is to use a graph diagram. All right. To do so, each node we draw as a, can you guess? A black dot, and each edge is what? A line segment connecting 2 nodes. All right. How many nodes do we have in this situation? Try again. Nodes is n, so we have 4, how many edges? 6. Let's go ahead and label them. Let's call this U1. Perhaps we call that U2. Perhaps we call that U3. Perhaps we call that U4. Connect them. Edge 1 goes U1 to U2. Edge 2 goes U1 to U3. Okay? 2 to 3 is E4. E5. Okay, so let's get into the matrix theory associated with this. And I think to do that, I probably should erase this board. In order to define matrices from today, what's the fundamental definition that we're using in this class to define matrices? So far, that definition 3.1. We define the matrix entry by entry. So let's define a matrix to capture the entire graph connectivity. To do so, we use an entry by entry definition. So let's go A, I, K. What are the different choices for A, I, K? Well, the claim is we're going to say the entry of the matrix in row I and column K will be 1 if edge I touches node K. Could you guess what we say if edge I does not touch node K? 0. Let's use this definition. And then the one claim was, what was the different conditions on I? In this particular example, how many values did I have for I? I's correspond to edges. How many edges do I have? 6. K's correspond to nodes. How many nodes do I have? 4. We're going to use what we call an undirected incidence table. Where the columns correspond to the nodes and the rows correspond to the edges, because the row index was corresponding to edge I and the column index was corresponding to column K. So let's take a look at this. What's the whole idea if I wanted to get 1, 1? 1, 1 would be the entry in the first row and the first column would be 1 if edge 1 touches node 1. Does edge 1 touch node 1? What other node does edge 1 touch? 2. So right there should be a 1. What about the other 2? 0, 0. What about edge 2? It touches 1 and 3. Everything else is 0. What about node 3? 1 and 4. Everything else is 0. What about node 4? 2 and 3. Node 5? 2 and 4. Node 6? Could you guess what A is, the matrix A? 1, 1, 1, 0, 0, 0. What's the next one? 1, 0, 0, 1, 1, 0. Then we got 0, 1, 0, 1, 0, 1. And then 0, 0, 1, 0, 1, 1. Claim the entire topology of that graph is right in that matrix. How many edges touch node 4? 1, 2, 3. Right? Which nodes does edge 4 touch? 2, and 3. Everything I need to know about that graph is now in that matrix. I could draw a graph just by looking at the matrix, and I would lose no information, right?